Good morning. Here we are once again. It's the physics video lecture, Psci 168, video lecture 25. The exams are not yet in, so we'll get those to you after the break. But I have some demonstrations for you. This is going to be about heat transfer mechanisms. The other day I actually did my little cartoon about heat transfer, and I wasn't sure if I had even introduced the idea yet, but in one form or another, possibly I have. So let's go ahead and get started. Heat transfer mechanisms. We've been talking about heat. We have the mechanical equivalent of heat, and we have thermal energy. The cartoon I had in the past was just, we named this thing Q, and we said it was, entering some body and it was changing the temperature. So we had Q equals mc delta T, where the delta T was a change in temperature. And I did indicate that if the change in temperature was negative, it meant the heat was leaving a body. And if the change in temperature was positive, we were saying that the heat was entering a body, right? This is M, mass of body. Okay, but you probably have to state, you can go back and state something even more fundamental. When the heat enters or leaves a body, it does that because there is what we say a temperature difference between two bodies. So we're going to talk now about heat transfer, and we can think of the heat transfer between one body and another. And the one with TH, we're saying that's the higher temperature, and the one that's labeled TC, that's the lower temperature. And the fundamental fact is that the energy flows from the higher to the lower temperature body. So yeah, high temperature on this side, and over here it's lower temperature. And it's always, of course, the relative temperature, higher, lower, and then energy flows from the hot to the cold. It'll take us a little while to explain how a refrigerator or a freezer works, because that might seem to violate this, but this is the situation. If you have two objects, a hotter and a cold object, put them in an ice chest, close the lid, and see what happens, okay? Well, this one's going to cool down, this one's going to heat up, okay? Eventually, you put them in contact together long enough and isolate them, they'll both be at the same temperature, so they'll end up in equilibrium. But until they get there, the energy is going to flow from hot to cold. So that's the first point of heat transfer. And the next thing is to talk about the mechanisms by which that can happen. There's only three, so this is an exhaustive discussion today. There are three heat transfer mechanisms. I'll put a word or two here. So, isolated system. That's the idea. You take both of these objects, put them in a cooler, close the lid. Okay, it's isolated. So you've got an isolated system. Energy flows from the higher temperature to the lower temperature object. So thermal energy moves from higher temperature to the lower temperature, to the lower temperature object. Good, so that's what we have for starters. So the next thing I'm going to do, I'll write 3 here before I erase the entire board, the mechanisms for that to happen. Question mark. And let me see, I Actually, I need a demo object. I'll be right back. Okay, it's all one take, no edit. These are two of my demo objects, but I have to come back for more. Okay, this time we're really back. Got some mystery objects here. All right. So, these just came out of a closet. They've been sitting on top of each other pretty much forever. And here's a metal rod. Okay, so next we have to talk about these mechanisms. I'll clear up some board. Okay, so heat transfer mechanisms. This metal rod here, it's got some paper wrapped on it. For the moment, it's just a big aluminum rod, and I'll just use it to illustrate a certain concept. So I fire up my torch, and I hold this thing here in the flame, and if I hold it here long enough, which I'm not going to do, but if I hold it here long enough, this end will eventually get hot. It would get so hot that I couldn't even hold on to it. That would take a while because it's pretty massive. And that's an example of heat transfer by conduction. So the idea is I have heat over here and it moves along towards this end. So I have the flame on this aluminum rod here. I better not grab the end, okay? That's called heat transfer by conduction. We actually have backstage, but I couldn't find it right now, a small version of this that's interesting because we'll have very thin wires, okay? And then instead of holding it in our hand, we'll clamp it and put a little plug of wax on the end, and then eventually the heat will come down to the end of the wire and the wax will get hot and drip off, okay? That's a good demo. In fact, that's something you guys could play around with at home. So heat transfer by conduction. Well, let's write that down and discuss it a bit more. So the mechanisms, I'll go ahead and repeat myself, heat transfer mechanisms. And the first one is called conduction. So conduction really operates, and so our demonstration, we have a flame, in honor of our butter candle. There's our flame, and we would have a wire or something, or an aluminum rod. A little color in the mix. Okay, there's our flame. And the conduction occurs from hotter to colder, just as in the cartoon I had up there. Inside are little molecules. They're becoming agitated and they're actually colliding with each other, and eventually the agitation, so the actual molecular motion that you can't see, is what what moves along this rod until the end is also hotter because the molecules are agitated. So heat transfer by conduction, we can also say it's by molecular collisions or something along those lines. And of course, it's always pH, thermal energy to the lower temperature side. Now a second demonstration, and this one is surprising, and you guys can do it at home, concerns these two pretty much identical in shape objects. This one is made of wood, this one's made of aluminum. They've been in the closet all day and all week, stacked on top of each other. What I do with the class, I pass these around and say which one is warmer, and this one feels a lot cooler than this one. You can hold it up to your cheek, definitely much cooler, okay? So, and yet they've been in a closet the whole time, and this should have turned into equality. So in fact, if you were to hold a thermometer up to these carefully, they would register the same temperature. Nonetheless, and we could say they're at room temperature. Now, this is what I'm going to carry up to the camera. Got to bring a tray or something. Doesn't matter. Okay, so here's what we're going to do. I'll bring these up to the camera in a moment, but I'll start them right here. I just put some ice on the wood, and I put some ice on the aluminum, and this happens so fast. Bring them up here. Bring them up here on this book. It happens so fast that you actually have to see it in real time. Okay, so I bring these up to the camera. Let's see here. There we go. I'll turn it around. What we have fantastic. Okay, this is the all-time convincer demo, really. What we have is an immediate puddle of ice water here. There's really nothing going on with the ice on the wood. The reason for that is that the aluminum has a high thermal conductivity, a high heat transfer rate. The wood transfers heat very poorly. Okay, before I get a puddle here, I'm just going to put this in the sink. Okay, fine. So let's do a little explanation of that, and this is one that you guys can do at home, and I'll explain how, and I think you'll enjoy that as well. So the second demonstration was we have these two identical blocks, and they have a little, they have a little circle in the middle. I'll just draw them here. A little submerged area, and I put ice in each one. Okay, so here was ice. This one was wood, and this one was aluminum. And it's really the most impressive heat transfer demonstration because the ice in the aluminum just immediately begins to melt, and at the same time the ice in the wood block has just left a couple of drops. In fact, this is almost completely dry still, and this thing had a full puddle of water in there. Okay, so that is because the aluminum conducts heat much, much better than wood. So aluminum conducts heat. So conducts, right? heat transfer by conduction conducts heat much faster. Okay, there are formulas to go with this. We're not going to introduce any formulas, but you definitely want to know these concepts. Heat conduction, so heat transfer by conduction. Internally, it's because of molecular collisions, and the effect is as I showed here. So let me put a recommendation up here for homework. The first thing, you could get a screenshot of what I just showed you and print it out. Screenshot. That would be easy to do. The other thing is you want to try it yourself. So you've got ice in the refrigerator, and you don't have to have any machined objects here. What you need is some different objects, and you can kind of set them up on a table and do an investigation. So let's see what do we have at home. So you have, so I'll call this the home experiment. So what do we typically have at home? Maybe we have a little cast iron skillet. I'm going to make a little list of things here that would work. Cast iron skillet, or some other kind of pan. Okay, so this would be cast iron. This would be another metal, maybe aluminum, maybe stainless steel. Okay, so what else do we have? A plate, ceramic plate, and cutting board. So for the wood, you don't need this, you just have a wood cutting board. So yeah, 3 of these 4, you'd have metal, ceramic, and wood, and you can do the same experiment that I just showed you with ice. You want to make sure each of your objects has just been sitting in the same place for a long time, so that they definitely all have the same initial temperature. And then then you do this experiment here, and start, and then maybe take a picture several minutes later, depending on how fast things are melting. So this also, images, and if possible, print it out. Print and include in your notebook. Okay, so this is a good one. This is a fun one, and people are surprised. Practical knowledge here, for example, if you're going to thaw out some meat or something, if you thaw it out on a plate or even something metal, but probably not on something metal, but if you do thaw it out on something metallic, it's going to thaw out much faster than if you just lay it on a piece of wood. Okay, so yeah, there's a good application, and that would be heat transfer by conduction. So that's our first important heat transfer mechanism. A couple demonstrations. So let's move on to the second heat transfer mechanism. And I don't have as many demonstrations for this, but this one's not bad. So basically I just take the torch and turn it on. Very hot out here. On the other hand, okay, it's very hot out here. Be careful. The blast. On the other hand, I can approach the flame with my finger very, very close, okay? I feel nothing right there. And yet I feel enormous heat out here. Okay, before anything bad happens. But that's a good demonstration. Why do I feel so much heat here and none right here? Same solution to both questions. Let's go ahead and erase this and put our second demonstration. And this one you can actually do without a torch. So we'll start just with demonstration is that we have a flame or square candle. What could be better, right? We've got a flame here, and it's very hot up here, so you can do this with a candle. Very hot up here, you can come in as close as you want to the side, or very close to the side. What's going on is that the air is being heated, and it rises, but more importantly, there's just an air current that's being formed. So we have something like this. A candle's actually better for this demonstration, so you guys should try this at home too. First of all, you light the candle, you can hold your hand above it, hold your hand to the side. But what's going on is that there's an air current being formed, and a current is a flow, and we refer to convection. So heat transfer by convection. That's just a current, in this case, a current of hot air that carries a lot of energy with it. But you see, there's a current being formed, and so it's always being replenished with cooler air from below. For one thing, that's part of the reason I can come this close. And the other reason is that the air isn't really heated here in any great amount, and the conduction through the air is very minimal. Minimal heat transfer by conduction in the air. Okay, but when it gets heated up a lot, it gets blasted up. You know, the current embodies quite a bit of heat. Okay. So that's the idea of convection. And the reason the candle's such a good demo is if you snuff the candle, you're going to see a rising column of smoke. Okay, and that rising column of smoke is really an illustration of that convection current. Okay? There are little tiny particles in it that you can see, but it's showing you the convection current. And in fact, so I'll put here note, snuff the candle, then what do you have? You need a little more room to draw it. Then you no longer have a flame, you have this little rising column, which in fact dissipates up there. That is actually showing you the current, the convection current. Okay. So it shows the convection current. That current was there when the candle was burning, you just couldn't see it. Okay. Shows the convection current. Okay, so these two transfer mechanisms, conduction and convection, they actually play a role together sometimes. I'm going to put this as a note. Conduction and convection. And I'll give an example. In other words, how they play a role together. If you have the wall of your house, okay, the wall of the house, so this is the wall, and let's say this is inside, this is outside. Go ahead and put a few more words there is what I'm discussing. This is the wall of your house, inside, outside. So say it's still colder outside. Okay. Still colder outside, therefore we would say we've got TH here, and we've got TC here. So if this is the wall of your house, it's still warmer inside, colder outside, then energy is going to flow through the wall to the outside. On the other hand, there's air inside, and air is not a good conductor, right? Aluminum's a great conductor, wood doesn't conduct that much. Air conducts even less. But you have a layer of air in here. I should actually expand this. I will, but I'll explain it right here. So you have a layer of air inside, which would be a great insulator. Good insulator, you know, poor conductor equals good insulator. Except for the fact that there's enough air there to start a current flowing. And what happens inside the wall is that actual convection currents will form. Okay. And these convection currents, which is air cycling around inside the wall, will actually carry the heat from one side to the other much more rapidly. And the reason that you see fiberglass insulation stuffed inside of the walls, if you ever watch a house being built, fiberglass insulation is stuffed inside in order to suppress the development of these convection currents. So conduction and convection are operating together here. You would have very little conduction, except for the fact that the convection current builds up there. Let me put a word or two about that. So I'll just write here, example. In the wall of a house. Of course, you could have a solid stone wall, solid concrete wall, and then you're just going to have conduction. On the other hand, stone or concrete conducts heat a lot better than air does. Okay? So the wall of a house, air insulates, okay? And so make a note, insulation means poor conduction, low conduction, but the air can circulate as well, and that's convection. But, it can circulate, and that's convection. Okay. I may return to that. That's a little, well, it's all, I said it all, but we could get a slightly better cartoon going. And we will. So yeah, we have these heat transfer mechanisms. We now have conduction, we have convection. And by the way, this actually leads to another topic. How can you suppress convection without using fiberglass insulation or styrofoam or something like that? You can also suppress convection if you want to suppress heat transfer by producing a vacuum. Like in a vacuum bottle, a thermos bottle, there's no gas inside there for convection to build up. So then you can suppress heat transfer by convection. Consult the clock here. Okay, so conduction and convection, there are many, many examples of those. So I'm going to erase this and just put a couple notes as to what I just said. So let's go returning to the conduction aspect. Conduction, and then we say conductivity is the property that an object has, that a substance has, how well it conducts heat. And I'll just go from high to low. Conductivity, high to low. We could take aluminum, and what we would find if we compared aluminum to steel is that steel has a much lower thermal conductivity, but downstream from the metals, we could have, say, glass has a lower conductivity, and then wood, and then we could say air, a gas. They all conduct heat, but this is the higher and lower, so high so there's our scale. On the other hand, if you're trying to suppress heat transfer, then you want insulation, and insulation, air is a good insulator, wood, air is the best, or vacuum. Can't put vacuum here, it has no conductivity, but yeah, we could go down the list and say vacuum, no conductivity at all. But it would insulate the best. So you'd have vacuum, and then air, wood, glass, steel, aluminum, very poor insulator, okay? So what I'll put that as a note is that a good conductor is a poor insulator. Okay, and vice versa. So good conductor, poor insulator. Sometimes you want a good conductor, sometimes you want a good insulator. Okay, so I want to get to the third heat transfer mechanism, and that's why I brought this light here. So I'm just going to describe my demo. Go ahead and erase. So third heat transfer mechanism. We'll start with a demonstration. So what do I have here? This is just a very powerful light bulb. Here, I'll demonstrate. Okay, very bright. And it is in a parabolic dish. And what I'm going to do is turn this light on and aim it over here. And here I have some matches. Okay. Some matches, and I intend to ignite the matches from a distance. Okay, because of the current situation, it's all just across the table. We can do it from a much greater distance, provided everything is set up right. Wish me luck. It's all one take, no edit. Okay, so turn this here. Uh-oh, I'm not getting the focus. Well, there we go. I wasn't quite in the focal point. I'm not going to repeat that, but that's a success of sorts. I'll explain the focal point in a moment. But yeah, we did ignite those matches from across the room. And there's a lot to discuss here. This is an incandescent bulb. These are parabolic reflecting dishes. And in fact, the two dishes here are actually the same. So it's out and it's out. Good. So that was apparently also a heat transfer mechanism because I ignited those matches from a distance. So ignite matches with light. And we have over here a parabolic dish. And there's a light bulb right here. I'll just draw it like that. Actually, it's parabolic dish, small light bulb. Okay. And we get some light out of this thing, right? And over here we have the same parabolic dish, and we have matches. Now in both dishes, the light bulb side and the matches side, the objects are at the focal point of this dish here, at the focal point. And the reason I had to adjust this a bit is because it wasn't quite at the focal point. But the definition of the focal point is the point where all the rays converge. So over here the rays leave, come out parallel, they're reflected, and then they all go to the focal point, which I should actually draw a little further away. I should draw this out here, say. Okay, good. Focal point of focus. Focus. And for that reason, right, all parallel rays go to the focal point. And so the heat is transmitted across a great distance. It doesn't need any air in between. The air plays no role. In fact, our sun transmits heat across millions of miles of vacuum. So it's a parabolic dish, same thing over here. The light bulb at the focus, the matches at the focus. So this is referred to as heat transfer by radiation. Heat transfer by electromagnetic radiation. So let's go ahead and write that down. And as far as this side being hotter, you can believe me, this is a very, very hot, it's still hot, okay? Light bulb gets very hot. In fact, I'll put here as well, just for the record, that's what's called an incandescent bulb. Okay. So we're looking at heat transfer by radiation. So 1, 2, and 3, conduction, convection, radiation. You'll never forget, right? Heat transfer by radiation here. So this radiation, not to be confused with radioactivity, this is electromagnetic radiation. That's fine. Electromagnetic, you guys thought it was just light. It is. So electromagnetic radiation is light. But it's more general than visible light. Visible light is just a very small part of the full electromagnetic spectrum. So that's the third heat transfer mechanism. There are no others. Conduction, convection, radiation. And this one's interesting because, and again, I'm not going to do the law of that, but suppose you have some temperature here, say TH, that just means it's high, it's warmer than the surroundings. So if this is an object, say a ball of metal, okay, a glowing ball of metal, red hot, it will actually be giving off electromagnetic radiation in all directions. But on the other hand, if the surroundings are warmer, it will be absorbing electromagnetic radiation as well. That's something that's present everywhere and all the time. Like I said, it doesn't need gas, it doesn't need air, it doesn't need any medium. So it can be transmitted across a vacuum. So you've also maybe heard of electromagnetic waves. That's what we're talking about there as well. Electromagnetic waves. Visible light is just a small portion of it. So you could have an object not giving off any light, and yet, any visible light, and yet it could still be radiating electromagnetic radiation. In fact, without getting too technical, the laws that describe this use the Kelvin scale. So even this chunk of metal, if it were, taken out of the freezer, less than 0 Celsius, it would still be, what's 0 Celsius? 273 Kelvin, and by the law of electromagnetic radiation, it would be radiating energy away. And if it were in a colder environment than 0, it would definitely be giving off energy and getting colder in that manner. So yeah, things can become hotter or colder in a vacuum away from anything by absorbing and reflecting electromagnetic radiation. So, absorbing and emitting. Okay, if they're emitting electromagnetic radiation, that's giving off energy, or they can absorb it. So that's a heat transfer mechanism as well. I think I'll just summarize those now. Consult the clock again. Yeah, for today, that's adequate. So let's just summarize once more. So we had this demonstration, and this is something you may want to look up, see if you can get some good visuals for your book as well. But got the heat transfer mechanisms, and now that we've seen them, so this is how we summarize this and file it away in our mind and move on. First of all, the law is that the energy goes from the higher to the lower temperature, and then the three mechanisms are conduction, convection, and radiation. So conduction, convection, and radiation. And I've given a demonstration for each. This is your molecular collisions, this is your fluid flow, and these are your electromagnetic waves. Okay, so we can even write that down. Collisions, fluid flow, and electromagnetic waves. We're going to study some electromagnetism as much as we can in the coming weeks, but we still have stuff to do in thermal physics. Yeah, and then if you're setting this up even more, then over here, you would be able to state some examples of phenomena of conduction, phenomena of convection, radiation. So you put your demonstrations and other interesting examples. For example, fluid flow, difference in temperatures. All of your atmospheric weather phenomena involve convection. Wind is a convection phenomenon. Towards the end of the semester, we're going to actually talk about wind energy, and then we're just going to be able to go back to this topic right here and make fast progress. Okay. And the sun shines, so the sun shines on our Earth, heats up the air, there are air temperature differences, we get convection, we get wind. It illuminates the ground, and so that's radiation warming the ground and any objects that are in the sun. And then once they're warmer, they can conduct heat to places that are not in direct contact or are not directly being irradiated by the sun. So yeah, a good example for all of these is just the sun irradiating the earth and just setting things in motion. Okay? And this is the abstract version, energy being transferred from the hotter to the colder. Okay, I'll leave it at that, and there's a spring break coming up, so enjoy that, and we'll see you next time.